Um, so with that in mind, we're going to look at these two different ways of adding vectors. So two questions for you. First of all is that the bird flies 3 meters per second through the air towards north. There's a wind blowing from west to east at a speed of 2 meters per second. It's worth knowing which direction is west and east on a compass. So as you're looking at a piece of paper, north is up, south is down, to the left is west, and to the right is east. Can you tell me the velocity of the bird relative to the ground, and can you tell me what that bird's displacement will be 20 seconds after we start our observations? Same question is that a rower rows a boat across a river at 3 meters per second. The river is flowing with a velocity of 5 meters per second. She's rowing directly across stream, well, that's what she's aiming to do. What's the resultant velocity of her boat? And you've got page 34 is where you've got space to answer those questions. So have a go at those, please, folks. We'll talk them through in a minute. Pause your video and then we'll talk them through. And unpause. Okay, oh, there's a picture of a boat. So how do you do this? You draw your vectors out head to tail. So this bird's going 3 meters per second north, 2 meters per second towards the east. Draw out the vectors head to tail. Use Pythagoras to calculate our magnitude. So 3 squared plus 2 squared is 4 plus 9 is 13. So the displacement is square root of 13. All my data skimmed to 2 significant figures, so I'm going to give my answers to 2 significant figures. So that's 3.6 meters per second. And then I'm going to use trigonometry to calculate my bearing. So I'm measuring this angle here, and tan theta then is 2 divided by 3, which gives me a bearing of 34 degrees, or 034 degrees. With this rower, it's a little bit more tricky. Distance, the displacement, if they're travelling at 3.6 meters per second for a time of 20 seconds, then 3.6 times 20 is just 72 meters. And again, the bearing that they're moving at is the bearing of their displacement, so 34 degrees. The rower rows a boat across a river at 3 meters per second. The river is flowing at a velocity of 5. What's the resultant velocity of a boat? This is easiest if you draw it out, actually. And you've got a big tip there, which is draw it out. If you're not sure, draw it out. So 3 meters per second across stream, 5 meters per second downstream. There's our resultant. Joining the start point to the end point gives us our resultant. We can measure that angle from the riverbank. If you have a look at your booklets, it's asking for degrees from the riverbank in terms of the direction. So we can find the velocity 3 squared plus 5 squared. Square root it, you get 5.8 meters per second. And the angle, tan theta, from the rule of z, that's this inside angle here, which is, so tan theta is opposite, 3 divided by adjacent, 5. 3 divided by 5, inverse tan, you get 31 degrees. That's great and all well and good. And when we've only got 2 different vectors that we need to add and they're at right angles, it's really easy. Pythagoras, you probably did in like year 8, year 9, trigonometry, year 9. So low level maths there. It's a little bit more tricky when we've got maybe something a little bit more complicated. So it might be the case that we've got a number of vectors that we need to add together and not all of them are at right angles. If that's the case, here's what you're going to need to get out. You need to get out one of these, which is a ruler. And somewhere in my desk here, I've got a protractor. And I need my ruler and my protractor in order to do this. So I'm going to set myself a scale. So let's have a look at this problem. We're going to use a ruler protractor, carefully draw a scale diagram, and then measure the length and angle of the resultant vector when we join the start point to the end point. So we've got a couple out for a walk, and they walk 2 kilometres due north, 3.5 kilometres at a bearing of 030 degrees, and then a further 1.5 kilometres due northeast. They then walk 2 kilometres due west. And this takes a lot of care and attention. So I expect this to take about 10 minutes for you folks to do. And when I next see you, I'm going to ask for you to show me your diagrams. In fact, I might put something up on Google Classroom asking you to take a photo of your diagrams and submit it, please. So draw a vector diagram, show the couple's journey, and work out the total displacement. You have to start at the bottom of your page, because if you look at this, most of their journey is spent walking north. So your starting point is at the bottom of your page. Work out a scale, I don't know, 2 centimetres per kilometre, something like that. Draw a straight line of the appropriate length. Use your protractor to measure an angle from north of 30 degrees. Draw a straight line of the right length again. Then you've got to use your protractor to measure 45 degrees, this due northeast, and then due west, work it through, see how you get on. We'll have a look at an example answer in a minute, but try it for yourself, please. Okay, I'm going to let you pause, and hopefully that's done now then, guys. So this isn't to scale, this is roughly the shape that your diagram should look like. So let's go 2 kilometers due north, 3.5 kilometers at bearing of 030, 1.5 kilometers due northeast, and then 2 kilometers due west. So you should have a diagram that looks like that. Your resultant vector, turns out if you do the maths, this is more accurate than you can get from this really rubbish diagram, is about 6.2 kilometers at a bearing of about 7.5 degrees from north. We'll have a look how I might do that on paper here. So this is just going through those questions that we've talked about so far. You should have these parts of your booklet complete. Your important rules when you're adding vectors: always add the vectors by joining them tip to tail. The order you do this in doesn't matter. And then you find your resultant vector by drawing an arrow, joining the start point to the end point. And it's always really useful having some real clear indication of which is your resultant. So here I'm making use of colour. For this presentation. If I was to do this with a piece of paper, I'd probably use a single arrow for my component vectors, the ones making up the total journey, and a double arrowhead on my resultant vector. Make it really obvious which is which. So we talked that one through. We've talked about the displacement bird, and we've also talked about the velocity of the rowboat. We've got 31 degrees from the riverbank. On here, I've chosen a scale of 1 centimetre is 0.5 kilometres, so 2 centimetres per kilometre. And then worked very carefully out. This is the diagram that I get, drawn neatly and tidily. And somewhere between 7 and 8 degrees measured by a protractor for my resultant. I find a displacement of 6.2 kilometres, a bearing of 0.07 degrees. I know that because this is 12.3 centimetres for my resultant, and 1 centimetre is half a kilometre, so 12.3 times by a half is 6.15. I'm going to give it 2 sig fig, so 6.2 kilometres. Okie dokie. So you are now all experts at adding vectors together. And there's an Isaac Physics exercise for you to have a look at. Isaac Physics B2, adding vectors, pages 41 to 43 of the topic booklet. Deadline's the end of the week for that, but the sooner you do it, the sooner it's done, and the better. Okay. Sometimes we're not interested in adding vectors together. Sometimes we've got a vector and we want to actually break it down into two components which are at right angles to each other. It's important. There are always components which are at right angles. So there's a video here of where and why we might want to do this and how we go about doing it, and then we'll have a look at some other examples. So here's a video.